In this PPT, we are going to deal with LPC2148 microcontroller. Right? Till now we are dealing with ARM microprocessor. Now we are moving on to microcontroller. So what do you mean by microcontroller? It is nothing but microprocessor along with some additional peripherals integrated into a single chip. So this LPC2148 is a microcontroller. It is having ARM7 TDMIS as the ARM core, ARM7 TDMIS as the ARM core inside this, and all the other additional peripherals are given by a company known as NXP. So NXP, what they have taken? They have taken ARM7 TDMIS from the ARM Limited. They have attached their own peripherals to this ARM processor and made a microcontroller and given a name known as LPC2148. LPC shows that it is a microcontroller from NXP. Previously it was known as Philips. So this is a LPC2148 architecture. It is having so many peripherals and ARM7 TDMIS as the core. So this is a most important part of the LPC2148 architecture. So you can see ARM7 TDMIS is the ARM core present in this controller. Then you are having emulation trace module. This is used for in circuit emulation, and this is for test interface. We have seen that it is having on chip debugging support. That means using the debugging interface, you can connect it to a debugging hardware directly. You can connect, no need of any other intermediate device, right? So this is your actual ARM processor, ARM7 TDMIS. This block is your ARM processor, and the other things are the peripherals, right? So how will you connect your ARM processor with the other peripherals such as timer, ADC, etc. by using something known as bus, right? And here in the ARM architecture, in this ARM architecture, there is a special type of bus known as Advanced Microcontroller Bus Architecture or AMBA Bus Architecture, AMBA, Advanced Microcontroller Bus Architecture, right? That is a special type of bus used in ARM products. And this advanced microcontroller bus architecture means, and this AMBA bus architecture, it is having two subdivisions known as advanced high performance bus and VLSI peripheral bus. So you AMBA basic ARM architecture, advanced microcontroller bus architecture is divided into two set of subdivisions known as AHP and VPP. AHP means advanced high performance bus, VLSI peripheral bus. Advanced high performance bus is used for connecting all the advanced peripherals such as your USB DMA, vectored interrupt controller, etc. This is used for handling all the interrupts. What do you mean by this interrupt controller? We will see later when you are dealing with interrupt. And so DMA controller, vectored interrupt controller, let us take these two are the high performance devices. They are connected to advanced high performance bus. And the peripherals such as ADC, external interrupt, timer, etc. These peripherals are connected to VLSI peripheral bus. So why it is connected like that? What is the speciality of AHP and VPP? AHP is a high performance bus. That means it will be operating on higher speed when compared to VLSI peripheral bus. So for example, you will be in your laptop, you will be having a processor, you will be having a hard disk. Processor will be always operating on a high speed. Hard disk will be operating on a low speed. So how will you read a data from hard disk to a processor? Directly you cannot read. Speed mismatching will be there, right? So here, so how will you read it? There is something known as RAM and then cache memory will be there. So a group of data will be taken from the hard disk to the RAM. From that, a group of data will be taken to a cache. From the cache, it is given to the actual processor. That is how the speed mismatch is handled, right? So in our example, let us take your hard disk. Hard disk will be connected to a low speed bus known as, say here, let us take it is connected, it is known as VPP, and your processor will be connected to, say, high performance bus through cache, something similar to that. So the high performance devices will be connected to high speed bus known as advanced high performance bus. All the low speed peripherals will be connected to VLSI peripheral bus. So how will you take a data from a low speed peripheral to the ARM processor? How will you handle the speed synchronization? For that, you are using this block. It is known as AHP to VPP bridge. So what does it do? It will convert the data which is sent from low speed devices which is connected to VPP. That data will be converted to a format that is acceptable by the AHP. Right. So AHP to VPP bridge will convert the data given by or sent to the VPP VLSI peripheral bus to the format that can be taken by AHP. Then from the AHP, how will you send the data to ARM7? Because ARM7 processor, it is operating on the highest speed. AHP is operating on next lower speed. VPP is operating on again lower speed. So how will you send the data from AHP to processor? For that, you are having AHP bridge. So AHP bridge will do the conversion of data from AHP bus format to the ARM7. Right. So this speed mismatch will be handled by AHP bridge. This speed mismatch will be handled by AHP to VPP bridge. That is how the data which is sent from the low speed peripherals will be sent to the will be sent to the processor which is operating on highest speed. Right. Then in addition to advanced high performance bus and VLSI peripheral bus, there is one more bus known as ARM7 local bus. This is the fastest bus available in ARM. So in ARM, you are having, if you are drawing three subdivisions, you are having ARM7 local bus, AHP bus, VPP bus. Out of this, ARM7 local bus will be operating on the highest speed. Why? You can see that it is directly connected or it is directly interacting with the processor ARM7. Right. So ARM7 will be the highest speed bus. Then comes the AHP. AHP will be connected to the high performance devices. So when you are comparing ARM7 local bus and AHP, AHP will be slightly lower speed when compared to ARM7. VPP will be the slowest bus when compared to this. And what are the peripherals connected to ARM7 local bus? RAM, SRAM and flash controllers. And a special peripheral known as fast general purpose IO. There is a normal general purpose IO known as GPIO. This is a fast bus. This will be around 2.5 times faster than the normal GPIO. That is known as fast general purpose IO. It is directly connected to ARM7 local bus. But the normal GPIO will be connected to VPP bus. Right? So in addition to fast GPIO, you are having SRAM controller and flash controller connected to a local bus because they are very important. What is the use of SRAM or what is the use of RAM? RAM is used for handling the data. Right? Right? So if you want to add two numbers, for example, where will you store the data? You can use the RAM for that. Right? So whatever data you need to manipulate, you can store it in the RAM. Say 1 and 2. And say you are performing addition, say add EQ R1 comma R2 comma R3. R1, R2, R3 are the registers used in ARM. It is known as known like that. So add is the instruction, right? And the data will be stored in the registers. So let us take data is stored in the RAM. So RAM is used for storing the data. So here you are having a special type of RAM known as static RAM. That is a normal RAM. So RAM is used for storing the data. Where will you store the program? Here program is add, or where will you store the instruction? That is add. Where will you store that? So the program will be stored in a separate memory known as flash. Right. So in this LPC2148, you are having certain KBs of flash, certain KBs of SRAM depending upon the serial number. In 2148, you will be having this much amount of flash. and this much amount of RAM, right? So this architecture block diagram is same for 2141, 4244, 46 and 48. Only there is a variation in the RAM size and flash size. So what is the use of flash? Flash is used for storing the program, flash memory. So initially, in the olden times, where was the program stored? It was stored in a place known as, or in a device known as ROM, read-only memory. What is the speciality of that? You can only read from that. You cannot write into that. After the invention of the ROM, they have developed something known as PROM, programmable ROM. That means you can write to that ROM only once, then you can read from that, right? So that writing process will be done in the factory itself. That is known as PROM, programmable ROM. Then after few years, EPROM was developed. That means you can erase that and you can rewrite it. How will you erase it? Using something known as ultraviolet rays, right? So there will be a separate EPROM eraser for erasing EPROMs. So how will you apply the ultraviolet rays to the data which is stored in the IC? So for ultraviolet rays, it is a light radiation. It is a light. So how will you take this light to the actual data present inside the chip? So for taking the light, if you see a EPROM IC, in the center there will be a transparent window. Through that transparent window, ultraviolet rays will be taken to the actual silicon chip sitting inside the EPROM. Right? So if you are seeing the old 8085 kit, there will be an IC where the company name will be pasted. Say VI Microsystems. One sticker will be there. So that sticker will be pasted on the EPROM. Why that is pasted? In order to cover that transparent surface. Otherwise, if some sunlight is allowed to fall on that, sunlight also will have certain amount of UV rays in that. So that UV rays may corrupt the data present inside the EPROM. So in order to avoid that corruption, one sticker will be pasted. So that IC is nothing but your EPROM. Then after few years, so here what is the problem? You need to have a separate UV eraser for erasing the program, and it will take around 20 minutes for erasing that EPROM. So in order to overcome, and since UV is a heat radiation, maximum you can perform only 1000 erase cycles. So 1000 erase cycles can only be performed. External additional eraser is required. So and 20 minutes it will take. So in order to overcome all this problem, E square PROM was developed. It is known as electrically erasable programmable ROM. This was developed. So electrically erasable means there is no need of UV eraser for that. Directly using the electrical signals, you can erase the program. So that was developed. So and there is a problem with the E square PROM, electrically erasable PROM. What is the problem is that if you want to write some data, you can write only first you need to write in the first register, first location, then you need to write in the second location. Like that only you can write. So bulk read and write was not possible. That is a problem. So in order to have that advantage, they have developed another type of ROM known as flash ROM. That is the latest one. So flash memory, bulk read and write data is possible. That is why in your pen drive you are having flash memory. That is a main advantage, and you can perform the read and write using the normal 5-volt supply, right? And you are having more erase cycles, around 1 lakh times you are having the erase cycles in this flash memory, right? So now you are using the flash memory for storing the program and RAM for storing the data, right? So these are the basic peripherals, and one more peripheral you will see. This is known as a system function peripheral. This is used for handling the clock input given to the controller. So whatever microcontroller or microprocessor you are taking, I told it is a complex digital device, right, which is working on a clock signal, or it is a synchronous digital device. It will be working on a clock. So how will you connect a clock? How will you generate a clock in your digital lab? You will be using something known as trainer kit. Inside that, how will you develop make the clock? Clock means the clock signal, you know, no? How will you develop that clock? By using something known as 555 stable multi vibrator, right? But the problem with that is that you will not be able to produce accurate clock. Say if you are in the case of your laptop, you are telling that say 3.2 gigahertz. 3.2 gigahertz means always processor should be getting 3.2. If it is varying, if there are some variations in the clock, the working will be affected. So the 555 stable multivibrator problem is that it is not accurate. Why it is not accurate? Because so many passive components are used for generating the clock. Because for making the stable multivibrator, you need to connect some resistors, some capacitors, etc. to the 555. So all these passive components will have their own tolerance. So the clock output will be slightly varied. It will not be accurate. So you cannot use that. So here in a case of microcontroller or microprocessor, how will you generate a clock? You are using a certain peripheral known as crystal oscillator. It is a small component. That component can generate accurate clock, right? So that crystal oscillator will be connected across this Xtal1 and Xtal2. So that is also a passive component. It cannot generate its own clock. So what does it do? From the controller, it will be giving say say for example say pilot clock to the crystal, or it will give a small frequency clock to the crystal, right? So whenever it is getting a small frequency signal, the crystal will start vibrating in its say fundamental frequency or whatever it is you can call like that, in the desired frequency. So if you are taking 12 megahertz crystal, if the 12 megahertz crystal is getting a low frequency clock from the controller, that crystal will start vibrating in a 12 megahertz frequency. So it will generate 12 megahertz accurate clock in this line. So the crystal oscillator will be having two inputs. One will be clock in, that is shown by this one. So it will be getting the clock in from the controller, and it will start vibrating in its own frequency. That frequency will be connected given back to the controller through this line, right? So this system functions block, it is used for handling the or connecting the crystal oscillator for the clock device. And it will be, and say for example you are using 12 megahertz clock, right? And you are having two PLLs connected to this system functions block. PLL means phase locked loops. If you are not studying now, you will be I think you will be studying in some higher semesters. For the in third or fourth semester, I think you will be studying this PLL. PLL means phase locked loops. It is used for multiplying or dividing the clock. So now you are connecting a 12 megahertz crystal. Let us take your processor should operate on 24 megahertz. What you will do? You need to multiply the clock by 2, right? How will you do that? By using PLL. So this clock multiplication is done by this PLL, right? So whatever crystal frequency you are getting, you can multiply the clock by using PLL 0, and you can connect it to system clock. System clock is connected to all the peripherals and the processor, right? So whatever crystal frequency you are giving through Xtal1 can be multiplied by PLL 0, and the output can be connected to processor and the peripheral. That we will see in another lecture how to configure that. PLL1 is dedicated for generating USB clock, 48 kilohertz USB clock. So PLL1 is used for generating USB clock. PLL0 is used for generating system clock. So this is a brief introduction regarding the LPC2148 architecture. Next we will see some basics of the PLL. So this is a PLL. So PLL will be having or PLL is used for multiplying the clock. How the clock is getting multiplied? Internal to the PLL there will be two sub blocks known as multiplier block and divider blocks. So this is used for the feedback. this is a multiplier. So you will be giving a clock input and you will give a multiplying factor. So if you are giving 12 megahertz, if the multiplication factor is 2, output you will be getting 24 megahertz. So how will the processor verify that you are getting 24 megahertz? This frequency out will be fed back to the input through a divider block. So this is act as a say feedback path. So by configuring the multiplying factor and the division factor, you will be able to configure the actual frequency output. You need to configure the multiplication factor and the division factor in order to configure this, right? So, and there are some limitations also. The input clock frequency of PLL 0 and PLL 1 should be in the range of 10 megahertz to 25 megahertz. So I told the input clock frequency you are generating using the crystal oscillator, you can connect only maximum of 25 megahertz. From 10 to 25 megahertz crystal only you can connect there, and this can be multiplied to a maximum of 60 megahertz. So if you are giving 12 megahertz, you can multiply it to a maximum of 60 megahertz. So maximum frequency output will be 60 megahertz, maximum frequency input will be 25 megahertz, and for USB clock it will be fixed 48 megahertz, right? And the multiplication of this clock is done by using something known as current controlled oscillator. All these things you will be studying later. So now you identify that the PLL will be having a current controlled oscillator which is performing this, right? So actually for configuring PLL in a programmer perspective, you need to configure only two things. What are they? Multiplication factor and division factor, right? So system functions block is connecting the crystal oscillator is connected to system functions. From that system function block, it is connected to two PLLs. PLL 0 is used for generating system clock, that is connected to processor and peripheral. PLL 1 is used for generating USB clock. So from the 12 megahertz crystal, you will be able to generate two different kinds of clock, right? Then next step is you need to calculate the multiplication factor and the division factor. How will you calculate that? There are two small equations for that. So here in this equation, say for example you need to generate a 60 megahertz frequency output. You are going to connect a 12 megahertz crystal. So from the 12 megahertz crystal, if you want to get 60 megahertz output, what should be the multiplication factor, what should be the division factor? That is calculated by using these two equations. So CCLK stands for core clock, that is a clock at which your processor ARM core is operating. In my case, my desired core clock is 60 megahertz, right? F oscillator stands for frequency of your crystal oscillator. In my case, frequency of crystal oscillator is 12 megahertz. So when you are connecting 12 megahertz crystal, how will you get 60 megahertz core clock? You need to configure the value of M. What should be the value of M? It should be 5. So M value is nothing but the multiplication factor. It should be 5. Similarly, you need to configure one more factor known as division factor, that is a P. Division factor. This is a multiplication factor. This is a division factor. So if you want to get 60 megahertz clock, what should be the division factor? This is the equation for that. How will you performing the division? By using the current controlled oscillator. So FCCO means it is a frequency of current controlled oscillator. There is a limitation for this also. The frequency of current controlled oscillator should be within 156 to 320 megahertz. It should be within this range, right? So this should be within this range. Core clock is 60 megahertz. So what should be the value of P? You need to calculate the value of P. So by calculating the value of M and by calculating the value of P, you can configure the PLL 0, right? Let us take one example. So this is example. F oscillator is 12 megahertz. CCLK required CCLK is 60 megahertz. So what should be the value of M and the P? What should be the value of M from this equation? Same equation. CCLK by F oscillator, 60 by 12 megahertz. You will get it as 5. How will you get the value of P division factor? The same equation. What I have only rearranged these two equations. The equation is same. FCCO by 2 into CCLK. What should be FCCO? It should be within this range. So first, what you will do? First you will substitute 156 in this equation. So P equal to 156 by 2 into CCLK. Desired clock CCLK is core clock is 60. So you will get it as 1.3. Similarly, you will instead of 156 FCCO, you will substitute FCCO as 320. So 320 by 2 into 60. So you will be getting 2.67. So what does it mean? Your P should be within 2.67 and 1.3. Right? M should be 5. So M I got it as 5. P also should be an integer, and it should be within 2.6 and 1.3. So there is only one integer between 2.6 and 1.3. What is that? It is 2. So if you want to get CCLK as 60 megahertz by connecting 12 megahertz crystal oscillator, the value of M should be 5, value of P should be 2. This is how you are configuring the PLL 0. Right? So now you have configured the PLL 0 to get 60 megahertz core clock. Then one more clock you need to generate from that. What is that? It is known as a VPP clock or peripheral clock, P clock. Why? Because all the peripherals are connected to VPP bus, VLSI peripheral bus. So you need to calculate the frequency of clock sent to that also. How will you calculate that? So by for that there is a block known as VPP divider block. Right? So the same C clock generated from the PLL 0 is given as input to VPP divider. So by configuring the VPP divider, you can configure the VPP clock. Right? So in my case, C clock will be 60 megahertz. By configuring VPP divider, you can configure the VPP clock. How will you configure the VPP divider? So whatever configuration you are going to do in a microcontroller, you need to configure some registers. So register is nothing but collection of flip-flops, right? And generally in a microcontroller, you will be having two kinds of registers. One is known as general purpose registers, another is known as special function registers. General purpose registers are used for storing or manipulating the data. Special function registers are used for configuring the peripherals. So if you want to configure a peripheral, you should use any one or more special function registers. Right? So configuring a register is nothing but register means what? It is collection of flip-flops. How will you configure a register? You need to configure a flip-flop. How will you configure a flip-flop? You by a digital value 0 or a digital value 1. So if you are writing a digital value 0 in a particular flip-flop of a register, it will be doing particular operation. If you are writing 1 in a particular flip-flop in a particular register, it will be performing certain other operation. So for configuring VPP divider, you are having a special function register known as VPP divider register. Right? And I told your ARM or LPC2148 is a 32-bit microcontroller. So LPC2148 is a microcontroller which is having ARM7 TDMIS as a microprocessor inside that. So LPC2148 or ARM, it is a 32-bit microprocessor. So ARM is a 32-bit microprocessor. LPC2148 is a 32-bit microcontroller. What does it mean? It can handle 32 bit of data. That means it can store 32 bit of data, or width of the data bus or the size of the data bus will be 32 bit, or it can handle 32 bit of data simultaneously. Right? That means all the registers which is registers are, I told registers are used for storing some kind of data. Since ARM can handle 32 bit of data, all the registers will be of size 32 bit. So here VPB divider is one of the special function register. That register is also of size 32-bit, right? In that 32-bit, for configuring the VPB divider, you are using only the first two bits, bit number 0 and bit number 1, right? So if you are writing bit number 1 value as 0, bit number 0 value as 0, that means you are writing 0 0 in these two bit locations of VPB divider. VPB divider is a 32-bit register, that means 32 bits you can write in that register. In that 0th bit location and the first bit location, you are writing a value or data as 0 0. If you are writing it as 0 0, what does it mean? You are configuring the VPB divider in such a way that you will be getting 1/4 of the C clock as P clock, right? So now your CCLK was core clock was 60 megahertz. So if you are writing these two bits as 0 0, your P clock will be 1/4 of CCLK. That means 60 megahertz by 4, so 15 megahertz. So by default, bit number 1 and bit number 0 will be written with 0 0. That is mentioned here. Reset value, what do you mean by reset value? When you are resetting the processor or when you are starting the processor, these two bits will be having these two values. That means by default, whatever core clock you are giving, that core clock will be divided by 4 and given as VPP clock or P clock. And by default, CCLK will be 60 megahertz, right? And how, if I want to configure this VPB divider with say if you want to make P clock as same as CCLK, what should I do? I need to write bit number 1 value as 0, bit number 0 value as 1. So if you are writing 0 1 here in VPB divider register, you are configuring VPB bus clock as same as the processor clock. So if you are writing 0 in this bit, 1 in this bit, what clock you will be getting here? Same 60 megahertz you will be getting. Similarly, if you are writing bit number 1 as 1, bit number 0 as 0, what you are doing? You are configuring the VPB bus clock as 1/2. That means if you are writing in bit number 1 as 1, bit number 0 as 0, 1 0, if you are writing in this register, your peripheral clock will be half of CCLK. So CCLK is 60 megahertz, P clock will be 30 megahertz. So by default, CCLK will be 60 megahertz, PCLK will be 1/4, 15 megahertz. Why it is 1/4? Because the reset value of VPB divider bit number 1 and 0 will be 0 0. If you are writing 1 1, it is don't care, right? So you can have 3 configurations for the VPB divider. This is very important because peripheral clock is connected to all the peripherals. So whatever calculation you want to perform on any other peripheral, you need to use this clock for the calculation. 15 megahertz, you should not use this. So till that you have seen the basics of ARM processor, LPC2148 microcontroller. Next we are moving on to the first peripheral known as GPIO. GPIO stands for what? GPIO means general purpose input output peripheral, right? So this is a peripheral, something similar to ADC. So it is a peripheral present in LPC2148 microcontroller, which is used for interfacing general purpose input or output devices. What are the input or output devices? For example, LED. LED is the simplest output peripheral output device you can connect it to this microcontroller. Similarly, can you tell one input device? Say switch. So switch is a basic input device you can connect it to a microcontroller. So if you want to connect input or output devices such as switch, LED, etc., etc., you need to configure general purpose input output peripheral known as GPIO peripheral. So this is the first peripheral you are going to see, right? So GPIO peripheral means it is nothing but, so general purpose input output peripheral is nothing but collection of pins, right? So LPC2148 is a 64 pin IC microcontroller. It is having a package known as LQFP, low profile quad flat package. Quad flat pack. Normally you may have seen DIP package, dual inline package. That means on both sides of the IC pins will be there. That is known as DIP. But your LPC2148 is coming under quad flat package. That means on all four sides pins will be there. And here it is coming, it is having special packaging known as LQFP, low profile quad flat package. Low profile means the thickness of the IC will be very less. That is known as low profile quad flat package. So it is a 64 pin quad flat package. This will be pin number 1. This will be pin number 64. So GPIO means it is a collect GPIO. We will be generally calling it as GPIO port. Right, so you will be calling the GPIO peripheral as GPIO port. So what do you mean by port? Port in this scenario, port means it is a collection of external pins. So GPIO port means it is collection of external pins. Why you are using? What is the use of these pins? Through these pins you are going to interact with the input or output devices. If you want to connect an LED, you need to connect it to a pin. If you want to connect a switch, again you need to connect it to another pin. So collection of pins, external pins shown in this red color, it is known as the port. Port is nothing but collection of pins, right? And in this LPC2148 you are having two ports. Port is named as port 0, port 1. Port 0 is having 30 pins, port 1 is having 16 pins, right? And I told port 0 and port 1, these are ports. Port is nothing but collection of pins. So how will you refer to each and every pin in a port? Say for example an array, you have taken an array of size 10. How will you refer to each and every element in an array? A of 0, A of 1, etc. Similarly here you are referring like this. P0.0 means 0th pin of port 0. Right? Similarly, P0.1 means first pin of port 0. So P0.25 means 25th pin of port 0. So this is how it is distributed, P0.0 to P0.25. This is how you are referring to each and every pin. Then P0.28 to 31. P0.26 and 27 is not there, you need to keep in mind. Similarly, in port 1, you are having pins from P1.16 to 31. P1.0 to 15 is not there. Why they have decided like that? Based on the chip manufacturer, based on so many criteria, power consumption, the size, based on all this criteria, they have decided on this many number of pins. That is done by the manufacturer. And you can see, so you can see here it is P1.20, P1.17, P1.16, etc. You can see that each pin it is written like, for example, P1 point, say let us take this P1.16 slash EINT0 slash MAT0 slash CAP0. What do you mean by that? Each pin is given multiple functionality. So actual pin number 46 can be configured as general purpose input pin P0.16 or external input pin, external interrupt pin 0 or match pin 2 or capture pin 2. That means 4 functionalities are multiplexed into a certain pin. Most of the pins are having multiple functionality. Why it is done like that? In order to reduce the number of pins, because if you are giving separate functionality to separate pin, more number of pins has to be there, so size will be more, power consumptive will be more, area of cross section of the chip will be more, so many parameters will be there. So in order to reduce the number of pins, they have given multiple functionalities to each pin, right? So this is a pin diagram showing general purpose input output peripheral of ARM7.